Title of my talk is the practical, resilient, efficient quantum key distribution. So there are three adjectives before we reach the noun quantum key distribution. And this joint work with my former student Shanton, who is now at Montreal, but actually he's finished his postdoc there and he will join his second postdoc in Germany with Professor Winter. So I would also like to acknowledge Professor Sushil Majumdar and his quantum optics lab at TIFR. It's just by talking to him that I realized that there is a big gap between what theoreticians like me would think of QKD, okay, and what the practitioners like Sushil do in practice, Sushil and everybody else. And these two sets of people usually don't talk to each other. And I realized there are many gaps between, and this work is an attempt to bridge that gap. Okay? And there's a hat tip to Bennett and Brassard, because it's thanks to them. And they were co-winners of the 2023 Breakthrough Prize. Okay, and the other two winners are also like people who everybody would know here, Deutsch and Shor. And I'll mention Shor once more in the talk. Yeah. Okay, so BD84 was actually first presented at a conference in Bengaluru, a IEEE conference. Okay, and the story is Bennett and Brassard met 6 months before that date, somewhere at a resort in Puerto Rico. Maybe there was a conference going on and they were swimming out there in the ocean or swimming pool or whatever. And they got thinking and then came up with these ideas, no proofs. Okay, it was presented in Bengaluru. This is a picture from them from much later in TIFR 2002. So the aim is to distribute the secret key securely in advance without requiring Alice and Bob to meet physically. I assume most people here are sort of familiar with what QKD is, so I'll go over it fast. So, this is impossible with standard, that is classical computers, because eavesdropper Eve is always listening. So think of the analogy, दीवार के कान होते हैं. Get more to that later on. It's possible, as they dreamt about, if Alice and Bob use quantum properties of photons. So in this talk, let us use polarization as the quantum property of photon, as the qubit, to exchange a secret key. QKD also requires a classical side channel, which we'll call a public authenticated classical channel. This is something that anybody can listen to, including Eve, but nobody can tamper. Okay. And the idea here is that the raw key is actually being sent through the photons, and Eve has to measure the photons in the quantum mechanical sense in order to get any information about the raw secret key. This will disturb the polarization of the photons, which will allow Alice and Bob to detect malicious activity. Okay, so again, I guess most of you are familiar with it. So this is just to remind you, like in BB84, Alice chooses a random bit. Alice chooses a random bit 0 or 1 of, we'll call it the raw secret key. But she also encodes it in a random encoding basis, which can either be the vertical horizontal polarization basis plus or the right left diagonal basis cross. Okay, so this is a schematic what's going on. Okay, so you can see Alice has chosen a bit sequence randomly. She has chosen a preparation basis also randomly. And then she encodes the bit 1 in the plus, so it's like the vertical. She encodes bit 1 in the cross, it's like the right diagonal, so on and so on. This is how it goes on. So there are 4 possible polarization states that are sent. They're sometimes called the 4-state protocol. So after Alice finishes sending all her photons, she shares a preparation basis with Eve. So she tells Eve this sequence with Bob, but Eve is listening. Bob, meanwhile, he has received the photons before, he has to measure them. He measures them in his own way, and we call it the detection basis. So this is another sequence of random basis chosen completely independent of Alice. So you can see in about half the location, the preparation and measurement basis agree. Half they do not. So these are the blanks where they do not agree. The locations where they agree, we'll call it the raw sifted key. And ideally, if Eve did not do anything, and the sifted location, Alice's raw key and Bob's raw key should agree. Note that sifting requires two-way communication between Alice and Bob, right? They have to exchange basis information both. Okay. So intuitively, why does this work? Eve can see Alice and Bob's basis because they're sent to the authentic channel, but she cannot alter it. So how do we ensure this? This is ensured by a classical crypto procedure called unconditional secure digital signature via two universal hash function. I mean, that's the mathematical tool used. But to actually do this with unconditional security, Alice and Bob have to share polylogin bits of secret key prior to this whole business. So as I said, दीवार के कान होते हैं, but if you remember the Dawn movie, lift के दीवार पे कान नहीं है. So Alice and Bob have met 10 years before in the lift and exchanged these polynomial bits. 10 years. They do the QKD protocol today, and if everything succeeds, they get n bits of secret. So really, QKD is secret key expansion. So it should be called QKD, not quantum key distribution, but quantum key expansion. Anyway, after this is done, secret keys are got. Alice reveals a small subset of a secret raw. So she reveals a small subset of that, and if Eve did not interfere, then Bob's outcomes will agree on that subset. So just to repeat, any attempt by Eve to gain information about the raw key means measuring the photons. So this will disturb the quantum state, and hopefully it will be detected by this agreement step during the reveal phase. So why did this all work? The point is, even after knowing Alice and Bob's basics and Alice's revealed sifted raw key, Eve has no control over Bob's measurement outcomes on the unrevealed photons. This is due to quantum properties. Note that Eve had to do her hanky-panky with the photons before all this preparation and measurement basis information was sent. So that's the key out there. Okay, so all this requires proofs, of course. So Bennett and Brassard gave no proof. But it turns out if Bob detects more than 11% disagreement, okay, he aborts the protocol. If the disagreement is less, he will continue the protocol. There will be further steps. And the assurance is that the below 11%, after doing the further steps, the final secret key will be unknown to you. And completely random. So what are the two steps? So this is the post-processing. So information reconciliation is the first post-processing step. It removes the disagreement between the unrevealed sifted key of Alice and the unrevealed sifted key of Bob. Okay. So we know it's less than 11%. So it will remove the disagreement somehow. To do this, Alice has to send some more information to Bob. Again, that goes through the authentic channel. So this makes additional information about Alice's unrevealed raw key base. And Eve listens to all of that. It can be done with one-way classical communication from Alice to Bob. So note that more of Alice's unrevealed raw key is getting leaked out. Something got leaked out because of this interference by Eve on these photons. More gets leaked out because of the information reconciliation step. So does Alice have any secrecy left? So it turns out in the mathematical proof is less than 11%. She still has some secrecy left, but this is to be extracted out. Okay. So privacy amplification extracts a smaller, fully secure key from the unrevealed, reconciled, sifted raw keys of Alice and Bob, and about which Eve has a non-trivial amount of information. So think about it that Eve has some function of the 11% amount of information about. So what is that function? Let's not bother with it now. But this can be done using another classical crypto tool called extractor. It can be done with one-way classical communication from Alice to Bob. All classical communication was the public authentic channel. So observe that the key was created with Alice and Bob physically meeting. This key can be used as a one-time pad. A little bit of it can be, polynomial amount of it can be reserved for a future group. So basically, because Alice and Bob have met in the lift 10 years ago and shared this polynomial secret key, maybe on chips or something, they can do this process later, and then this will bootstrap itself. So the complete mathematical proof of all this is highly non-trivial. It was first given with this 11% figure by Shor and Preskill 12 years after Bennett and Brassard. Yeah. So anyway, 1984 BB84 protocol, 1996 Shor Preskill security proof. So what are we doing today? So the thing is, there's many a slip between the cup and the lip. So QKD protocols, just as I described, and even the others, are usually designed for ideal single photon sources and detectors. So let's get into it. So now this is where all this engineering and practicality will come in. So what happens if, let's ask first the question, what happens if Alice and Bob cannot trust their equipment? Worst step, what happens if Eve has quantum correlation with Alice and Bob? So this can be addressed. This leads to what's called device independent QKD. The BB2 that I described is not device independent, it is device dependent, so DDQKD. But there is this whole line of beautiful theoretical research called DIQKD. So I'll not get into that. I mean, they basically use CHSH inequality, all these Bell inequalities to do the trick. The thing is, there's a parameter there called robustness. So they do some tests, some analog of Bell tests, okay? And they will see what are the errors in those Bell cells. So let's call that fraction P. Like this is like the bit flip error. So those Bell tests failing. Now, DI-QKD protocols have awful robustness. So for it, most of them don't bother to publish actual numbers of the robustness that they can do. I mean, it's clear that there is some constant. They say the constant is very small, but how small? So Buzzy and Bennett, one of the earliest DI protocols, actually published a number. They came up with an erratum also of that which lowered that number. So the final correct number which they claim is this 0.6%.
This robustness and Q bar is same.
Q bar?
Q bar means quantum bit.
Yeah. It's the same. Yeah. Okay. Now, another thing is this photon challenge. Like you are going to send the phone, they have a large number of mutations. Even the very best means you have to use proprietary Chinese technology. So they have around 7 to 8% mutations. Okay. So, I mean, you can see.
Means photon loss.
Yeah, photon loss. Yeah. So, yeah, radiation is the name in classical information, photon losses. Yeah. So, most DI protocols require Alice and Bob to have quantum memory before they do the CHSH and all these other bit flip tests. Okay, so they will create a lot of repair pairs. Alice will have to store one half and then do something and send the other half. Okay. So this storing photons is infeasible in practice. Remember, photons are particles of light. If they're not really stored, then they run away at the speed of light. Okay. So it turns out that the Vazirangvidic DI protocol can be, as written, it looks like it requires quantum memory, but it can be re-engineered to have no quantum memory. They can prepare one EPS pair and Alice sends one half to Bob and proceed that. So it's possible. But still, we have this no bit flipper. Okay. Enough about DI-QKD. Let's come back. So DD-QKD at this short Preskill is assuring me 11%. Let's see how good that is. So these are called prepare and measure type protocols. So Alice prepares a polarization, sends it to Bob, Bob measures. Prepare and measure. So let's say Alice and Bob use trusted shielded devices so that Eve cannot tamper her photon source or Bob's photon detector. Alice and Bob don't need quantum memory in the prepared measure types, but remember the devices are far from ideal. So let's understand this in more detail. An ideal single photon source correctly produces exactly one photon of the desired polarization with probability 1 on demand. You ask the source to produce, let's say, horizontally polarized photon, it produces exactly one. Perfect. Yeah, on demand. Ideal single photon detector, given the correct measurement basis, will correctly measure the polarization of the photon with probability 1 on data. Ask it to measure. If there's a photon, it will measure it. If there's no photon, it will say no photon with probability 1. These are the ideal things. But the real single photon source on demand produces photons with probability not 1 but B. See that B is actually much less than 1. Now, given that it produces photons, more than one photon is produced. Also, it's a single photon, but there is a probability G where it produces more than one photon. They will all have the same polarization. Now, the produced photon should have the desired polarization. You ask it to produce horizontally, better produce horizontal, but maybe there is some error so that the overlap is Q. Okay, could be 1, but it can be slightly less than 1. So there are names given by the experimental to this. G called the purity, Q is the quality, B is the brightness of the source. And ideally, you want the quality to be close to 1. The purity probability of producing multiple photons should be close to 0. For most real photon sources, if you want these parameters, high quality and low purity error, then the brightness becomes very small, around 1%. So this means that you ask the source to produce your favorite horizontally polarized photon, it will produce nothing. You have to ask it 100 times or even more before it produces something.
But then there's a crucial question: can you detect that it's
yeah, you can. So maybe I'll cut off later, but yeah, very good. So there is a class of real single photon sources called heralded single photon sources. Yes. So they produce a photon, which is the quantum bit, but they also produce a classical bit on the side. If that's called the herald. If the herald bit is 1, that means there is at least one photon.
Actually, you still can't.
There's that G there, no? Yeah, there's the G. You can improve it. There are sources with photon counting detectors, but they lead to other external problems. Okay, so if you want, let's say, good quality real single photon sources, you can get that, but you have to pay the price that there is this probability G of producing multiple photons when the Herald bit is.
Like many sources together so that you get at least one of them will succeed.
Yeah, so that's called multiplexing. People do that. So you may not be able to multiplex 100 of them, maybe you multiplex 10 of them. But as you see, is that the brightness is not really an issue. I mean, the naive idea of trying many times, if done with a little bit of care, will give a practical protocol which has fit. Okay, let's move on to the detector. So the real detector will detect a photon if it is present in probability E. Okay, given that the photon is detected, and we are assuming it's measuring the correct polarization basis, it detects the correct polarization. So let's say it's working in a diagonal basis and the photon is right diagonal polarized. It will detect right diagonal polarized with probability C.
Again, if I go to interrupt. So for the you say G, right, for the probability that more than one, but is there like a cutoff that you know that it will produce at post 5 photon that just goes all the way to
it's like a probabilistic. It's a probabilistic.
spontaneous parametric down conversion, right? So there's a nonlinear crystal, so that you can actually calculate the probability of having the gain photon. And that drops.
Yeah, so you can say it drops according to the Poisson distribution. Okay, but the Poisson distribution technically goes on to infinity. So
that's what I was trying to answer. The the analysis, like arbitrary dimensions, because you're going to get a device dependent players.
Yeah.
And then you have to worry about like one of the extra, you have to worry about.
No, so we'll take the conservative. We'll say that when it's extra, there are infinitely many extra. Okay, and we'll prove security against that. So yeah, super powerful. It is given all the benefit when the benefit is there. Okay, so coming back to the detector, if there's no photon in the detector, it will say there is no photon with probability 1 minus. Okay, so there E is the efficiency of detecting the photon, C is the quality, detects the correct polarization, D is called the dark count. Okay. And ideally, this should be near 1, no dark count. No? Yeah. Okay. So, so this is answering your first thing. How does Alice generate uniformly random Rocky and uniformly random preparation base in the event? Okay. Okay. So the naive method is this: use a heralded single photon source, which I just explained, with passive control. So passive control is you design the source in a clever way, and you don't use an explicit random number generator. So as Shantanu said, I mean, this is the spontaneous parametric downconversion source. You put some mechanism of beam splitters below it at the right angles. So you can ensure that this crystal is producing one out of these 4 polarization states with probability 1. So it's great. I don't need a random number generator. Okay, my source is doing the job. So that's called passive control. Okay. And yeah, the herald, as I said, is a classical weight which tells if one or more photons are produced. So the problem with passive control, so this is a very engineering problem, is that Eve can do a detector blinding attack. So she will shine a powerful circularly polarized laser beam towards the ball. Remember, the 4 polarization states are vertical, horizontal, right diagonal, left diagonal. The circular polarization, whether it's left circular, right circular, that actually has an overlap of half with all these 4 states. Yeah, I mean, people who know, I mean, these are the 3 mutually unbiased bases in 2 dimensions. Okay, so you will choose one of these circular states, and essentially what happens is, again, because of the physical properties of Bob's detector, Eve can force Bob to measure the basis of these terms. And after the basis shifting step, which Eve is listening at, Alice and Bob are left with exactly equal shifted Rocky, but Eve knows everything about it. And Alice and Bob are blissfully unaware that an atom is. So there are, engineering fixes also. They'll say, oh, Bob will have a brightness detector if he sees very bright light being put off. But then there is always the iffy thing. Okay, so the brightness detector will have a threshold. What happens if Eve is shining laser light close to that threshold? So Bob doesn't know what to do. Eve gets a non-trivial amount of information, maybe not all the information. Security starts going for it. Yeah.
So who's producing the performance? Alice.
Alice is producing.
Bob is detecting.
Bob is detecting.
And he is going to shine light on Bob's detector.
Yeah, and Eve will force Bob to measure in the basis dictated by Eve, not by Bob. See, okay, so the detection is also done passively. So maybe that's it. No, so I mean the way I was described, Bob chooses the measurement basis and then measures, right? No, so this is the case when you say passive control. Bob also measures passively. So there is a way that Bob doesn't choose the measurement basis, but you're set up with that crystal and all. Ideally, we'll choose the plus or the cross basis at random and then measuring that. You know what basis it has chosen, and afterwards, yeah. So this is a passive detector.
This sort of passive thing is susceptible to circular waves. Right?
Yes. So these are cheap ones. Okay, and initially they seem great and they're doing the job. I mean, you don't need random number generator. Okay, but then you can do this detector blinding attack. So these are called the bright light attacks, and there's a class of them. So it can sort of start controlling Bob's measurement basis to some extent.
So why is it called a bright light attack? I thought it's circularly polarized digital one.
No, it has to be powerful enough to. There is a blinding. I mean, yeah. So Eve is not sending one photon; she's sending many photons. But the point is, see, I mean, if a detector cannot detect the difference between 1 photon and 10 photons. I mean, there are photon counting detectors, but they have much lower efficiencies. So yeah, so what are the ballpark figures? If you use the ones available in the commonly available in the market, so silicon-based detectors, the efficiency is like 60-70% at most. Okay, but if you want to go higher, so that you approach ideally, you need the superconducting detectors. Okay, so they will have efficiency upwards of 95%, 90, 95, even higher. Maybe. So the thing is that if you're using the superconducting detectors, they cannot detect the difference between 1 photon and 10 photons. Okay, so you will have to put some separate filter to measure the brightness of the light to prevent. And these are closures, but then you will work at that threshold. So remember, in cryptography, Alice and Bob have to publish their entire protocol to the whole wide world, and then Eve has to break it. So Eve knows exactly what are the specifications of the brightness detector and you play around that. So this is not a very secure thing. The way out is Alice uses active control. So active control is exactly what I described earlier for the ideal description, where she classically chooses a random Rocky bit and random polarization bit. So this requires random number generator. Okay. She will use a heralded single photon source, of course, as before, but now she dictates the source, like produce right diagonal polarized. Maybe make 100, but please produce them. So that's how this will go. So we'll talk more about the random number generator. Okay, how does Alice handle small brightness? As I said, by making many attempts. So let's say she makes A attempts. Each attempt succeeds with probability B. If an attempt succeeds, as indicated by the herald bit, Alice stops trying. So probability that Alice fails even after A attempts is just a simple expression. And then how will we do it experimentally? Alice and Bob will use synchronized clocks. Each time window is big enough for A attempts. Alice aims to send only 1 photon per time window. And Alice also sends the herald bit across to Bob in each time window. So even if Alice succeeds in creating a photon early on, remember, let's say the time window is big enough for 200 attempts. Suppose she succeeds in creating a photon in the 10th attempt. She will just cool her heels till the entire time window goes. This is there so that Bob knows which photon is for which thing. There's no out of time thing out there. Okay. So the thing is that what happens if even after A attempts, Alice has not succeeded in producing anything, okay, that will be treated as a photon loss or as an erasure. Okay. The protocol will take care of it. So by taking the number of attempts sufficient large and if you have sufficiently good channel and all, then the detector efficiency is sufficiently close to 1. We can ensure that the erasure probability, which we call S here, is unchecked. So 10% erasure is possible in state of the art. So Chinese technology is claiming 7 to 8% erasure in free space over moderate distance, maybe 1 and by the way, they are far ahead of anybody else in the world. So even 10% is hard to get, but it's possible. And another advantage of Alice sending the herald bit to Bob is that it avoids dark count. So if Bob detects a photon but the herald bit hasn't turned on, clearly dark count, so you don't have to bother about it. Okay, so how does Alice handle the quality not being one? So what was the quality? Alice wants to send, let's say, vertical polarized state, but what is produced is something slightly different from that. The overlap is slightly less than one. That's okay. I mean, Alice really does nothing. So, but if your hardware is good and the source, the detector, limited interference, so what this will show up, this overlap not being one, it will show up as the bit flip error, which you call P. Should be small, close to zero. So remember, earlier P was the amount of disagreement in the reveal phase between Alice's revealed raw key and Bob's corresponding locations. Okay. So yeah, so with good hardware, 1% is achievable in state of the art. But this 1% is achievable even with the Bazaro silicon detectors and all that. Okay. So really, the issue with the real implementation are other iterations. These split flip errors are quite rare. So it will turn out that the protocol should be able to handle a limited amount of bit flips. I mean, Shor and Preskill ideal case 11% bit flips. How does Alice handle purity not being zero? That means more than one photon is produced. Okay. Yeah. So, so what Eve can do in this case is what is called a photon number splitting attack. Another engineering attack, but this is one of the deadliest attacks there. So what Eve does is she siphons off all but one of the photons within the time window. These extra photons, all of them have the same polarization as the original photon. So Eve will perform measurements. Remember, we're taking conservative. She has infinitely many extra photon. She measures and perfectly figures out what is the raw key with there, what is the preparation basis used. Okay. And Alice and Bob are blissfully unaware of it. So this is, I mean, as you can see, pretty deadly. This is even more severe if you don't use true single photon sources, but what are called weak coherent sources. So these are basically highly attenuated laser pulses. So they have, you ask the laser to send a pulse, the mean photon number in that pulse will be like 0.1, 0.2, 0.2. So you ask it again and again, and hopefully some photon goes. But then if you do that Poissonian calculation, there is a significant probability that more than one photon is produced. So yeah, so these are not so good. So we will stick to the so-called true single photon Heronde sources. But for that also, there is some purity. So 1% is good.
So I have a small question. So you said that in the photon number splitting attack, right? You were saying that eventually Alice, sorry, Eve can use infinite photons. I didn't fully make the connection. I thought it was.
So in one window, see, in one window, one raw key bit has to be sent. Ideally, that one raw key bit is encoded into one photon. But because
you think that the source is maximally bad,
yeah,
so it's producing infinite.
Yeah. So so let's say 10 photons produced, he will take away 9 and just send one at once. Very powerfully, but yeah. Remember, we want to prove security against the most powerful. So the thing is that 1% of these attempts which succeed from real single photon source, 1% of these attempts which succeed will succeed with more than one photon. So this, we cannot really mitigate. The protocol should be able to handle this loss. We have to put it into our analysis. Okay, so the protocol needs to be practical and resilient. So practical means it should work with these real single photon sources. It should be designed taking all these parameters into account. Resilient means that the protocol should be able to handle many more erasures as compared to bit errors. Okay. So sometimes it's easy, sometimes it's not. So usually erasures are much larger than bit flip errors. More importantly, you should be able to handle small non-zero purity loss. Okay. And let us say 10% erasures, 1% bit flip, 1% purity loss is the typical value of state of the art. That's the protocol should work. Now, it turns out that two-way communication protocols like BB84 can be implemented to be practical and resilient. So for erasures, what Bob does is Bob points out the erasures during the basis setting step. So in addition to finding out the disagreeing location, Bob further says these locations are in. So this is what all the experimenters were doing. I got interested in this. Like I was talking to Sushin and he said so many losses. So I said, what do you do with the loss? Oh, I just throw them. And work on the result. Is that secure? This thing isn't it?
It's not necessarily.
That's not necessarily secure, okay. But it turns out if you study the Shor and Preskill proof and rework, you can rework it against arbitrary number limitation. So no explicit literature, at least in the theoretical literature, talks about this. But yeah, so I guess it's folklore or something. The Shor Preskill proof can be reworked to handle any amount of relations. Okay. So that's fine. Now, now, what about imperfect random number generators? Right? Remember, we're doing active control, so we have to do a random number generator. So I'll talk a little bit more about it later. But what we'll do is that, so you'll say, okay, quantum random number generator and all that. But remember, no random number generator is perfectly uniform. So, but here we have a nice computer science solution to it. So take two of them. And the assumption is that these two are independent, which is probably a pretty fair assumption. I mean, you take two different hardware generators with two different technologies. Neither of them are independent. Neither of them are perfectly uniform, but they each have enough mean entropy given the side information. Remember, now the side information is a quantum. So I'm talking of quantum side information. And in fact, E has joined some information on both these random number generators, giving Eve all the power. The only thing is that despite Eve, condition on Eve side information, source one has some linear mean entropy, let's say more than 50% mean entropy. Source two has more than 50% and they're independent of each other. Under this assumption, we have deterministic two source extractors. We apply that. What you get is a smaller random key, which is now independent of the same.
The independence has to be its once you condition on Eve.
Yeah, once you condition.
Is debatable two-way communication or what?
Yeah, because basis shifting style, there's a lot of two-way communication.
And two-way means like, I mean, that is two paths, right? I mean, where you can tap.
No, so Eve's quantum tapping is only one way. The photons are going one way.
One way.
Yeah.
That's
The two is the classical way because Alice is to send a preparation basis to Bob. Bob is the other way. Other than that, photons going one by one, which happens right at the beginning. After that, everything else is classical. So the first thing in BB84. Yeah. So I mean, this is the first communication. This is photons. They go from Alice to Bob.
right.
But after that, there is classical communication. Alice sends her preparation basis to Bob. Bob sends measurement basis back.
You're calling that two-way communication.
Yeah, I'm calling that two-way communication.
No, actually, there are several two-way QKD protocols, like LM05.
So, when they talk of two-way, they talk of the privacy implication after that. They sort of believe that Alice and Bob have to exchange this. So
Yeah.
as I said, I mean, there are enough things like this on the carpet. But now, here I'm being brutally honest. I mean, if it is two-way, definitely Alice has said something to Bob, Bob has said something to Alice. Maybe several times also. So the fundamental two-way is this exchanging the basis. So information reconciliation and privacy implication can be done in one-way fashion from Alice to Bob also. There are protocols which try to improve them by doing two-way communication. So if you talk of one-way versus two-way QKD, it is that part which they are playing. Typically the privacy amplification. And sometimes in information reconciliation. I'll mention some of those jargon and maybe you will be reminded of what is one-way, what is two-way. And I will mention that. Okay. Yeah. So we can put this two source extractor, get basically almost perfect random numbers independent of E. But unfortunately, no earlier work has done a detailed quantitative analysis of even BB84, good old BB84 with all these parameters.
I have a silly question eventually. So these, if you have these two sources, is there a way to test independence obviously, or you have to just
believe that? You have to believe. So there was a debate we had this, well, by now maybe a month back or something on a WhatsApp group of quantum people in India. Is there really a black box way of testing randomness? And I was arguing that there really isn't.
I said,
yeah, there is a device independent, but I'll tell you, the problem is even in device independent.
or you assume something.
Yeah, you assume because you test a subset of that, where you're getting the randomness from. I say that there's absolutely no
Application.
Yeah.
You have some.
You have to assume something. Yeah. And I mean, see, and the thing is, experimentalists have heard these terms from theory, and they say, we have certified randomness. Ask them, they'll say Topli's metrics. Ask them again, two universal hash function. Then I'll say, but you have to choose a random hash function. Where does that randomness come from? Then so, yeah, we didn't think of that. You have to assume that. So that's why I said, what you do is a deterministic two-source extract.
And if you trust your device, then maybe you could just take like a weave script.
Yeah. So one of the quantum random generators is basically a deep split operation. Okay, but the point is that the deep splitter may not be exactly the 45 degrees. So what you're getting, okay, is there is enough entropy you're getting. So it's very close to the 45 degree. Yeah. So you can easily assume that it has mean entropy more than n by 2. Okay, but it's definitely. I mean, I'm not assuming it's n. Maybe really speaking, it's 0.99 n, but it's there. And if you take another chip, maybe even with a different technology, just to be sure, that's also 0.99. They are independent of each other. That's what we need. But that independent we assume from white box analysis. You open the box, look at the circuit diagram, whatever, put shields around them. Yeah, that's the assumption. So my aim is to, make out computational assumption, random assumptions. Bring them to light and clearly say where we will assume assumptions from engineering and physics. Beyond that, everything will be done rigorous. Okay. So all this is fine, but there's also another issue that QKD protocol also needs to be efficient.
So in the one of the parameters was saying how many extra photons are going right in like probably G or something.
Yeah.
And you earlier mentioned that you're going to assume the worst case in the sense that you're going to assume that you can make the detector such that it's essentially sending the photon. Yeah. But here you're now going to restrict it, I guess, to G.
No. So what it means is that in 1% of the cases where photons were sent, infinitely many photons were sent.
That you remember.
Yeah, that's the assumption. Okay, so that again is a belief we have in our photon sources. Okay. And the belief is also that, so that's basically the belief. Yeah, 1% will happen that way. So Eve can adversarially dictate which locations send multiple photons. We're even giving it that much power. Our protocol will be able to handle that. But yes, not more than 1%. Okay, so efficient. So what does efficient mean? That the computational steps of the protocol, the classical computation, essentially the post-processing, should run in time polynomial in n. Let's say n is the number of final bits of secure secret key that you want. So the thing is, if all these quality parameters lie in the allowed range, the protocol must abort with negligible probability. Right? We want the protocol to be useful. It cannot always abort. Okay, and the security loss of the final secret, we say should be uniform and independent of E. Of course, it's not going to be perfect. There will be some silent distance from ideality. That should be negligible. Okay? Negligible means less than inverse polynomial in N for N. That's a standard security parameter cryptography. Okay. And honest part is Alice and Bob should work on only one photon at a time. There should be no quantum memory. So unfortunately, the information reconciliation step was never rigorously proved to be both correct and efficient. So correct means, it should reconcile and it should send the information to the minimum, or else you're not going to get that 11%. So I need that, and also I need it to be efficient. This was never proved. So, so various heuristics exist, like LDPC codes, they will say cascading. So cascading is this two-way method of doing information reconciliation. So it's essentially like binary search. Think of it as binary search. You want to find the locations where Alice's and Bob's log qubits disagree by binary search. So that's basically there's a cascading is two-way, LDPC is one way. That what they mean is the information reconciliation done by LDPC is one way from Alice to Bob. Cascading is two-way between Alice. But they have not been rigorously shown to achieve that claim percentage. Okay? And moreover, all these things have mostly been analyzed for IID errors. So they assume that Eve is acting in an IID way, but actually Eve's corruption is adversarial, not IID. So that's also, there's a gap. Okay. Now, some of you may say that, there's the work of Renato Renner, where he applies some big theorem called exponential definity theorem, and he converts any error into IID error. Okay. So the thing is, if you really look at that properly, so he uses the definity theorem as a big hammer. So it's used to prove security. By security means he finds what is the amount of mean entropy left in Alice's raw key bits, given everything that has gone over the classical channel in Eve's interference, okay, everything that has occurred so far. So the definite theorem, which reduces Eve's arbitrary attack to an IID attack, works for that part, to lower bound the median flow. But that definite theorem doesn't give strong enough bounds for the information reconciliation. So now if you go back and look at when Reynolds starts talking information reconciliation, he doesn't make unconditions. He said, if the error is binary symmetric channel with crossover probability P, then blah, blah, we can do this, do that. Okay. So I mean, he doesn't explicitly say that my theorem doesn't work, but to read between lines and work through the proofs again, it's pretty clear why that is. So that's why I say that there is no rigorous proof of information reconciliation, which is both correct and efficient. Okay, so in this work, we actually achieve provably correct and efficient information reconciliation suitable for QKD. Okay, and our information reconciliation method sends only one classical message from Alice to Bob, and then is the information going to add. So more on that later. But the biggest contribution is something else. Okay, so this is a question: can a practical, resilient, efficient QKD protocol be one way? Now, when I'm talking one way, it's honest one way. Okay. All communication is from Alice to Bob, even the classical post-processing. There's no basis system, no two-way reveal phase. Okay. Only the only two-way reveal, Alice reveals a little bit, Bob, one-way reveal. Not even acknowledge from Bob that he has received all the expected. Yeah, so I mean, you can say these are important for some military situations, so on and so forth. Okay, not bother, but it's a curiosity. Can this be made one way? Now, resilience becomes a major problem for one-way protocols. See, in two-way, Bob could communicate the locations of erasures back to Alice. The big advantage. But one-way, Bob cannot do that. So essentially, your information reconciliation has to do an extra role of even correcting for the erasures. So you need better error correcting codes behind that. Okay. And remember, erasures are much more common than bit flip errors, maybe 10 times as very common. So actually, in this work, because of our additional insights, so we can achieve a practical, resilient, efficient one-way QKD protocol for the first time. So it again turns out that the DI QKD protocol of Gaussian building can be modified to one way. As written, it's not one way, but it can be reworked to be one way. But remember, I mean, 0.006. Now, if it's one way, they have to take care of both erasures and bit flips. Big pain. Absolutely impossible.
So I have a question. This is, I think, in the earlier two-way, correct me if I'm wrong, but I guess at that point you could handle arbitrary number of variations, right?
Yes, with two-way you can handle it, but
here it's probably not.
No, it's not.
No.
The bound will come. It's not arbitrary. Yeah, but that's the price you pay for being one.
Just making sure I'm following it.
Yeah, sure. Good. So our main new idea, okay, is a quantitative extension of no cloning. So kind of, I mean, maybe a more philosophical thing. So there was a belief in certain section of QKD community that quantum key distribution is a kind of a result of uncertain relations. So people have written papers saying proof of security of BB84 from an uncertain relation, entropic uncertain relation. Then they also talk of mutually unbiased bases and uncertain relations. Okay, so there was a belief that this QKD is occurring because of some kind of fancy uncertain relation. So our observation is that this is actually not the case. QKD is occurring because of no cloning. Oh, spam. Oh. Let's say spam. Okay. So our work shows that QKD is occurring because of no cloning. So the main new idea is a quantitative extension of no cloning. So what do you mean by that? Let's say Alice does a naive encoding. She encodes her raw key bit 0 as the vertical polarized state, 1 as the horizontal polarized state. That means she's only using the vertical horizontal basis. Okay, very stupid thing. Now suppose somehow God ensures that Eve's action, all the Eve's tampering, is guaranteed to introduce less than Pn errors. Remember, P was that bit flip thing. Is guaranteed to introduce less than Pn errors in the computational basis, vertical horizontal basis, as well as less than Pn errors in the diagonal basis. Suppose this guarantee or certificate is there for you. Then NP is small enough, below 11% or whatever. Okay. Then Alice actually can do a naive encoding. She doesn't have to bother them with the diagonal basis at all. She'll always work in the plus basis, computation basis. She does a naive encoding, and that's it. I mean, you may think that I'm saying something is purely wrong, but think about it. So let's say Alice just does a naive encoding. So it's okay. He will copy out everything with the control dot operation. The control dot operation introduces Z errors. Okay, 50% Z error for each control dot. So if Eve is copying out all the bits, so it's n by 2 Z errors. That's not allowed.
You're taking P and N to be certain value.
Yeah, let's say P is 11% what showed this thing. Okay. Yeah, so that's the point. The thing is that copying out by control dot, the naive thing actually introduces Z errors, and we have a certificate. Okay, that's why we have this in the cross basis. And we have this in the plus basis also. Yeah. So again, come back to this later.
So isn't like almost an entirely classical argument? Because like you're coming classically, you're sending classical information and you're saying you can't even classically copy. So that doesn't sound like very impressive. I'm misunderstanding it. So,
well, yeah, it's not depending on that. I'm saying the whole Euclid is an elementary business. So I mean,
no, I thought you were trying to make a point that somehow it's any relations to work.
yeah. So it's really, I mean, preventing cloning. That is Euclid. Okay, but we'll see the benefit of it. I mean, absolutely. I mean, a very simple statement. Okay, I mean, okay. So essentially, people have been thinking Euclid to a very high. I think it's not. Okay. So, what we'll see the benefits of this viewpoint. Okay. So, right, the main observation. So there was one part about efficient information reconciliation. This is the part about a new security proof. Okay. So, in the new security proof, we have to make this first observation that this naive encoding will work provided Eve's action is guaranteed to introduce less than P errors in plus spaces and P errors in the diagonal basis. Okay. Yeah. Okay, so
guaranteed less than
no, less than this. No. You want Eve to introduce less errors, so she can copy less. I mean, if she copies k bits, then there are k by 2 Z errors. So k by 2 errors in the diagonal bits. Very short. Okay. So the new protocol uses the same for polarization states as BB84. It has similar steps as in BB84, but there are some notable differences. So first of all, we leverage. Remember, we want to get 1 bit. So we leverage those polylogin bits of prior secret key, which they had exchanged 10 years ago in the lift. We leverage that also. So earlier it was only used for the digital signature. But once we have that resource, we'll also use, we'll of course use it for digital signature, but we'll also use it for other things. Okay. So the point is even BB84 actually had this, I mean, to do the signatures, but now we use it for other things. Okay, so how our protocol starts? First of all, Alice chooses a uniformly random raw key of some capital N, which is maybe 1,000 times small n bits. Small n is the final amount of secure key you want to extract. You have to go some constant times that. Yeah. What she does is she translates her raw key, or you can say shifts her raw key using another independent uniformly random string of n bits. This is not the basic sequence. Think of it as another n bits of second block, and then you shift the first raw key by this. So okay, this is the translation string, which will later be revealed to Bob. So he will also look at that. Okay. Okay, so she first of all translates a raw key using another uniformly random string. She permutes the bit positions of a raw key by a permutation pi. At the moment, think that it's a uniformly random pi. Later, we'll remark that it can even be made pseudo-random. Okay. So the difference is if it's a uniformly random pi, then to permute n locations, you need n log n bits. But if you do it pseudo-randomly, this can be brought down to linear number. So that's the only reason for doing it pseudo-randomly. Okay. Then she uses part of the prior secret key. Okay, so one part was used for signature. Another part is used to choose polylog locations of a permuted translated raw. Only these locations are encoded in the diagonal basis. The remaining, okay, are encoded in the plus basis, and then Alice sends these photons. Okay. So remember there was the raw key, it was translated, then it was permuted, and then encoded. Almost all of them are the computational basis, the plus basis, only polylog and the cross basis. This polylog is chosen from the prior secret. Actually, it turns out BBA-T4 also has a similar translation and random permutation system. I mean, not the way they published it, but if you want to get all those 11% parameters and all, the way Renner does it, he has both of them. And Renner needs the random permutation step. For him, he needs uniformly random permutation because he wants to apply different vector. And for really the proofs to work nicely, at least for the maths to be nice, you need the similar translation. So actually, Renner has both those. So it's not that we are introducing overheads here. Okay. In particular, if you don't do the random permutation step, the tolerable bit error rate goes down to half of 11%. So actually, all of Shor Preskill's paper is basically aiming for 5.5%. At the very end, if you see, they have one very quickly like this. This is 5.5%. But what we'll do is we will permute the bit locations before doing the code at the very beginning. And this permutation will, of course, later be sent to Bob so that Bob knows which bit is which. But we'll do this permutation. If you do this permutation, then it looks like they are IID errors, so it becomes 12. It actually doesn't without. As we will now argue, is that this remark saying that it becomes IID is actually wrong. But nevertheless, still we are going to get 11%. Okay, so channel needs do their losses and interference, whatever. Bob measures the received photons according to the same basis sequence. Okay. Remember, what is the basis sequence? Mostly the plus basis. Bob just needs to know which has the cross basis, the diagonal basis. But Bob knows that because Bob also shares the prior sequence. So he already knows that in one. So he knows where to exceptionally measure in the diagonal basis. He notes of the positions of the erasures and the measurement outcome of the non-erasure. Remember, he cannot send anything back to Alice. He just notes that down for his postprocessing. Okay. Alice waits for a time delay. Okay. If why is this time delay there?
Could you say a bit about what the mission is for translation? I don't think
maybe I'll answer that later. I see. Okay. I'll answer that later. It's a more technical thing, but yeah. Okay. But at least you can see the permutation is needed to approach IID.
Yeah, how that is.
Yeah. So yeah, the translation for more technically more involved in the calculation. So I'll answer that later. But just remind me if I forget. So so I'll just wait for time delay. Why is there normally in the two-way thing, Bob will send a bit back to Alice saying I received all the photons. Here is not allowed that. So we just assume there's a time delay. Now the thing is, if there's no if, all photons minus losses will have been received by Bob within time t, and photons not received till time t. Maybe some photons are received later on because they are tampered or something. Then we treat it as relation. Just to remember that. All the 10% erasures covers even that. Okay, so what this protocol will do is that if Eve has done a lot of tampering, Bob will realize it and what? Alice will not know that. You can say it's a little bit unsensitive, but at least Bob is not fooled into something. But that's the best you can achieve. Okay. Or you can say that after that, Bob sends that one bit back. Okay. So remember, first the photons were sent. Now let's see what are the communication. First the photons were sent, but they were sent after creating the raw key, translating it, and permuting. Then the photons were sent. Then Bob has done the measurement in the right basis. After that, see, Bob still cannot make sense of it because he doesn't know the permutation, he doesn't know the translation. So Alice will send like linear bit classical messages describing the permutation. The header books, that's also important. Don't forget them. And the string for translating a raw. So of course, this uniform and random permutation, this should have been n log n, but because of pseudo-random, this is also n. The others are clearly n. Then Alice reveals polylog n bits of a raw key. Again, depending on another part of the prior sequence.
So the error bits are like for the cases where there was no photon, but maybe Eve injected photons. So space in the
yeah,
photon splitting and then
photon splitting will not be detected. You have to absorb it in the bounds of it. It's never really. Okay.
How is we detect the photon? Because we're using some sort of signature.
No, signature is only for classical measure. You can introduce a photon.
Okay.
They'll show up.
Okay.
Yeah. They will show up as bit letters. So that has to be less than that 1%.
Okay.
Yeah. Okay. So on this reveal set, Bob will estimate the fraction of X and Z errors. Errors in the diagonal and the computation basis. Okay. Bob estimates that. So Bob knows what is S and T. Note that Alice does not know SN. After that, Alice sends another linear number of bits for information reconciliation. The exact number I'll tell you later. That's the information query. So she sends another linear number of bits for information reconciliation.
What is SMP?
S is the number of erasures,
Oh,
and P is the number of bit figures. So Bob is estimated from that revealed thing. He keeps it for his post processing. That is required for Bob. But Alice doesn't know that. Just pointing that out. I mean, Alice can assume some guarantee that S and P are small. They satisfy something, but she doesn't know the exact value of S. Okay, so privacy simplification. So because we're polylogging bits, we can use yet another part and do privacy amplification. Slightly non-trivial thing. Instead of the favorite universal and hash function, we can use Trevisan strong extractor, which is secure against quantum side information. So the seed length is only polylogging. All classical messages are digitally decided, so this prevents woman in the middle attack of E1 classical messages. But she can inject photons, they'll show up with bit errors, no problem. Okay. Yeah. So that's it. I mean, it's all one way. Okay. So that what is the performance? If the parameters are in the allowed ranges, channel losses are small enough, these interference is small enough. Okay. The protocol aborts with negligible probability. If it does not abort, Alice and Bob's final secure keys, which is after privacy verification, they're equal, uniformly random, secure. That means essentially independent of E, except with negligible probability. So the protocol is efficient. All steps run in deterministic poly and time. I will have words to say what is the constant multiplying that n also. Yeah. Like what is the erasure probability? So there's the contribution. So this is even after the A attempts, nothing was sent. There is channel loss. Maybe E further creates some loss, and then there is the efficiency loss because of imperfect detection. The bit flip probability is there's some quality problem at Alice event. She did not produce the correct polarization. There's channel noise. There's Eve's interference also. And then there is also a quality problem with the detector and did not detect the correct polarization. All that you add up. So let capital N, as I said, be the number of bits of raw key, and there is this thing. So look at this thing out there. So in the next slide, I will discuss more. I mean, explain what is parameter, but there is some equation out there. If this inequality holds, then there is some amount of mean entropy left in Alice's unrevealed raw key base. Okay. And this is left even after all the side information Eve has got. The channel. After information reconcile everything. Okay. So that can be extracted. And so how large capital N has to be depends upon the failure rate. Yeah. And again, to repeat, Alice only sends n photons one by one, which will be measured one by one by Bob. And they need zero quantum N. Okay. Yeah, I'll come back to that formula because that's the main thing. Okay. So some more about the computation steps. Okay. So we take several steps for maximum efficiency. So the aim is that the engineer should actually do this. Okay. So the important part is the provable and provably correct and efficient information reconciliation. So the information theoretic minimum bits that Alice has to send to Bob. So Alice has to send this another one-way message to Bob. The information minimum is basically this. So where does this come from? So this is basically the damage caused by E. So the damage caused by E is S fraction of erasures. So to supply that. The damage, then in the unerased locations, the damage caused by E is P bits. So if you have to specify the locations, there are basically the amount of description length is H, the entropy. So overall, the damage caused by Bob by S erasures and P bit flips, okay, entropically is characterized by this term. So this is the additional thing that has to be sent from Alice to Bob. Okay. So this can be achieved existentially if you just choose appropriate random function as a hash function. Okay. I mean, in fact, information people will call it source coding with side information. Okay, so usually it was analyzed for IID channels. This is the formula that you would get for IID channels. We don't have IID channels, but thankfully the same formula holds. I'll tell you why maybe a little later. Okay. But remember, we have to do this efficient, that exists in not. So to do this, we need some fancy stuff. So this is all stuff which has been done by very, very smart people in coding theory, very different communities. So, unfortunately, I was not aware of them for a very long time. It took me 1 year to even hunt these results and understand them well enough. So, the first thing we need, remember, Alice does not know SNP. Bob knows SNP because he has done the testing on the revealed. So, Alice has to find one code which will work against a family of channels with varying SNP. So, of course, SNP have to satisfy that constraint in that equation, whatever. So, there's basically a continuum of channels that Alice has to fight against. She has to send one code which fights against a class of channels. She doesn't know which channel is going to be used by Eve adversarially. This channel is not IID. Makes sense. Okay. But remember that permutation was used to basically make it permutation. So this is basic. This is where the permutation is important to put some sanity into. To check Eve's malicious action. So what we know that the error channel introduced by Eve is a permutation invariant distribution from a family characterized by SNP. SNP unknown to Alice, of course known to Eve, now known to Bob. So this is called the compound channel information theory. And it turns out Hassani and Arbanke have given a efficient code called the polar code for this compound channel. Exactly under assumptions. Alice does not know the channel. Channel comes from a known family, and Bob knows the channel. Okay. So our codes that you have to use for information reconciliation, these are concatenated codes. So the inner block is this Hassani-Arbanke polar code for the compound channel. In the outer code that we have to use, okay, turns out Reed-Solomon is not the correct code for that, exceptionally. So actually, one of the reasons is that the length of this polar code, right now think of it as just a constant, large constant, but just a constant. And in Reed-Solomon codes, the inner blocks have to be length log n, or else you cannot construct. Here we need the inner block to be constant. So that's one reason, technical reason why it's not Reed-Solomon code. But it's better. I mean, so it turns out we can use a linear time code of Guruswami and Indic. So this is based on expanders. Okay. Then polar codes are again usually analyzed for IID channels. The effective channel for information reconciliation is not IID, but it's permutation invariant. And what I just said, I mean, the unknown SNP, but decline a family. Okay. But it turns out that polar codes, though they are analyzed for IID channels, also work against permutation invariant channels. Same guarantees. Okay. This is because, I mean, polar codes just work very well. I mean, their error rates are low, and then, I can tell it offline. There's a certain domination argument you can give for probability distribution. So it's basically out of the box polar codes work. And once inner blocks are decoded by the polar codes, now a few of them can be bad, right? I mean, the adversary may choose to concentrate the errors in a few of the blocks. So the decoding just goes back, polar code goes back. So to correct it, we have the outer code. So the outer code is in the Hamming sense. It will correct worst case, let's say 1% worst case errors. This is it for that. But it should be efficient, and in terms of we can do it in linear time. There's a question of what are the constants multiplying, that n in the order n. Turns out they're not, if you work hard enough with Guruswami indicate, they're not so bad. So that's the code.
So you just explained it, I think I completely understand. So why are we using concatenation and not like a single code? I think you said something about
single. Okay, so the only single code you could potentially use polar code, because it has to work for this compound channel, right? Okay. And so I can use a polar code for the whole thing, but polar codes, have a fair amount of overheads. Okay, polar codes are technically encoding, decoding is n log n, but that constant multiplying that order is fairly large. Okay, so I'll say more about that with concrete numbers. How large can that?
So as far as security is concerned, you
would have done that. Yes. So this is precisely for engineering. I could say polar code I've done, like n log n I'm done. Okay. So, but it's just for the engineering that I'm doing this. This is reason one. Reason two is if I make the whole thing a polar code, then I have to use a perfectly random permutation. So that's the n log n overhead. Whereas if I break it up into chunks, okay, I don't need a fully random permutation. So that's another advantage. maybe, a less important advantage, but yeah, that's also there. Okay. So all this was done on the assumption that they met in the lift 10 years ago and had this prior secret key. Suppose that is not available. Then what do you do? So people say, we have to use authentic channels, so you use the post-quantum cryptography, computational digital signature, but with post-quantum cryptography. Fine, do that. But even then, we can say something interesting. Remember, good old BB84 said Alice has to send n bits of basic information to Bob. Bob has to send n bits to Alice. We realized that that's not the case. Remember, only polylog of these things have to be in the cross basis, the diagonal basis. So it turns out Bob will just choose square root and polynomial size subset of locations in the diagonal vertices. Bob does the same thing independently. By birthday paradox, there are two subsets will agree in a polynomial locations, and that's it. So even the basis shifting step gets simplified by this very simple observation that it's no problem. Yeah. So as I said, all the randomness with the Alice is coming from this two source extractor. So again, yeah.
Like how will Alice know the parts where Bob's bits also agree? Because
no, Alice doesn't.
Oh.
Yeah, but that's the whole point. Alice keeps sending information. It's Bob who does all the post-processing work. Bob knows. So yeah, maybe wanting the curtain. So in the reveal phase, when Alice, so in the reveal phase, Alice reveals a polynomial size subset that is independent of this basis agreement thing out there. Okay. And the point is the reveal is only done on the locations which are encoded in the computation basis, the plus. The cross base is only there to limit. Okay. And the reveal is only done on the plus. And of course, when he does the error estimation, you have to do it both on the diagonal and the computational basis so that it's less than P in both. But yeah, the reveal is only done in the plus basis. Yeah. Okay. So yeah, so this is something I've showed before. So the idea is that all this happens because of this new no cloning style argument. So this is actually just elementary linear algebra, simple dimension counting. I mean, you model Eve's action as a big fat unitary on the send photons and her ancilla, and then just write down the state in a certain basis, just count the number of terms. So it's basically dimension counting, but this gives us a fantastic insight. Okay. This says that Eve's knowledge about the raw key bits is limited by the number of send errors. So this is the formal version of saying that all that Eve could do was copy with control dot. So Eve's knowledge about the raw key, in other words, the secrecy loss or the mean entropy loss of Alice conditionally is only coming from the number of errors. And information reconciliation is when Alice and Bob's raw key bits are different. That is coming from the X errors. So we have to bound both because we have to bound the secrecy loss and we have to bound the number of excess so that information reconciliation can go ahead. So this proof actually separates out. Early, there was no such separation. Now we clearly know where Eve is getting the additional information. Note that the X errors are also being done by Eve. But it's as if, okay, like Eve says on the third bit, put the not bit. But Eve doesn't know what the third bit was. Third bit has been flipped. But Eve doesn't know what to handle. So that gets quantified. That the damage for information reconciliation is coming from the NOT gates, that's the XLS. But Eve's knowledge is coming from the copy, which is the ZLS. Okay. Yeah, so then, it's a general thing that if you minimize the classical communication overhead, you minimize side channel attacks. So, this is related to remark, like in one of the early implementations of BB84, in fact, in Montreal, in Brassard's lab. So they had single photon sources. Those days they didn't have proper single photon sources, so they were using short laser pulses. The thing is that laser source made a different noise when it emitted a photon with different polarization. Okay. So Brassard made the remark. This is like a side channel. He said, okay, yeah, this is secure against an adversary who is there. So yeah, so if you have to minimize that, you need these overheads. Okay. Yeah. So yeah, the pseudo-random family of permutations brings the overhead decimal permutation down to n from n log n. So it's done using standard de-randomization techniques. I'll not get into that. Okay. So finally, so this is also a slight computation improvement. This is the first time that the classical communication overhead is linear. Okay, so this is our master equation. Now let's analyze what this is saying. Okay, the left-hand side, it's 1 minus something. Look at the minus something. That something is the damage caused by Eve and all this purity loss. That's basically the damage. So there's some damage coming from the purity loss G. There's some damage coming from the erasures. What is theta? Oh, theta is the little bit of slack that I have to put in. So this theta will play a role in how much larger the Rocky has to be with respect to the final. So let's put theta equal to 0. So yeah. Okay. So S is the loss due to the erasures. Then one further losses on the unerased locations, which is 1 minus S. There are bit flip errors. Okay, so to specify the location, I'd argued H of P, but in reality, there is also the photon number splitting. So the photon number splitting appears in 2 places. One is it acts like an erasure in some sense, but it also acts like a bit flip. Yeah. So in the actual analysis, they have to do H of P plus G. So this is all the damage created by, this quantity from G minus S. This is the damage created by eavesdropping and photon number splitting. So 1 minus the damage is the amount of mean entropy left in Alice conditioned on E. Yeah, there's the juice there. That's the left hand side. Right hand side is the additional amount of secrecy loss due to information reconciliation, which we argued before. Specify the location of erasures, that's S. In the unerased location, they have to specify the bit flips, that is H. So if the left hand side is larger than the right hand side, there is still some mean entropy left in Alice condition on E, which will be extracted by the extractor, privacy and location. Now let's look at what numbers we get. So think of an ideal setting where the purity loss is 0. Suppose there are no bit flip errors, P is equal to 0. And let's say we set theta equals 0, and that was the part of the slack here. Then we see that the number of erasures is less than 0.5. So in the ideal setting with no bit errors, the one-way protocol can tolerate up to 50% erasure. So this is consistent with actually a more plebeian use of no cloning theorem. So there are theorems saying that no quantum code can tolerate more than 50% erasure. That's why in the no cloning. So this is consistent with that viewpoint, similar to that. On the other hand, back to the ideal setting, so G is 0. Let us assume that now there are no erasures, but only bit flips. So we get this, and this gives speed less than 11%. So we recover what BT84 did. And now the gap between the LHS and RHS of this inequality, I call it SCR. This is really significant for engineering practical, efficient codes for information reconciliation. So what the slack does is it allows us to sacrifice the final secure key rate. Okay, so let us say the gap between this was maybe 0.2. So you think that 0.2 n is the amount of mean entropy that it can extract. So what I'll say is that no, I don't want to extract 0.2 n, I'll extract 0.1 n. Okay, so I'll sacrifice some of the slack, extract 0.1 n. But because I've sacrificed this, this allows me to use shorter polar codes. And remember, there are overhead to the polar codes. I'm really aiming for that. So this block length of the polar code, is the main computational intensive parameter for information reconciliation. So we want to make the slack as large as possible to get polar codes of the shortest block. So let's look at some numbers. Okay, so as remarked earlier, like 10% erasure, 1% bit flip, 1% purity loss is possible with state of the art. Let's say we relax it to 2% bit flips, 2% purity loss, and 15% erasure. So what does it mean practically? This means that Alice and Bob can be further apart, slightly more noisy channel and so on. Yep. Let's fix some small theta and all that. Then You put the numbers here, and you can see left hand side is this, right hand side is this. There is the slack. Okay. So yeah, fine. Our QPD protocol will work. It will extract theta n 0.01 and there. Okay. So everything runs poly n time. Note that the slack is 0.334. Left hand side minus RHS, fairly large. Let's see what this buys us. So the length of the inner block, where we are using the polar code, is very sensitive to the slack. Let's call it epsilon. So if you use a traditional polar code, so the traditional polar code is basically when Alice knows what is S, what is P. Okay. In the one-way case, she doesn't, but in the two-way case, Bob will inform her what is S and P. Suppose Alice knows that. If in the traditional polar code, this is the block length by the best polar code. Okay. For the strict one-way protocol, Alice does not know S and P, so we cannot use the traditional polar code. We need the Hassani-Armani polar code for the compound gel, and the slack is like larger. The block length of the polar code is larger. It's a worse function of the slack. So for, let's say this sample figure of the slack, this bounds look like about 200 for the traditional polar code and 40,000 for the Hassani-Armani polar code. So let's say a few hundreds, if Alice knows what is S&P. If Alice does not know what is S&P, maybe 1 lakh, 2 lakh, something like that is the minimum block. Now, these block lengths are moderate constants. Even let's say 1 lakh moderate constant. But the point is there are linear number of such blocks in each code, and n is the growing parameter. So, and the way you decode it, you first decode the inner blocks, independent of each other. And that's a constant, right? Either 200 or 40, whatever you take your pick. So we can speed up the coding, encoding, decoding by using FPGA. So that can actually lead to significant practical speedups. And this show the Chinese have already done this. Okay, but they did not analyze the polar code very rigorously. So we have scope for some work. Okay. Okay, the polar coding algorithm has a recursive framework. That's why you can get n log n and large amounts of parallelism. So lends itself well to an FPGA implementation. Okay, so if we move on to the linear time outer codes, okay, so Guruswamy Indic outer codes, so these are based on expanders. Okay, these codes also have a significant amount of parallelism. In fact, the Guruswamy Indic algorithm calls as a subroutine another linear time coding algorithm by Spielman. It's called many times. And Spielman algorithm is highly parallelizable. In fact, in his paper, he comes up with very efficient parallel circuit code. This is something that can be exploited computationally. Also, the Guruswamy Indic algorithm, besides calling Spielman, it also calls as a subroutine another constant length code. This is constant length, maybe like 10,000, 100,000 length code. So, depending upon, again, the slack. So again, because constant length, you can speed it up by an FPGA. Okay, so then as I said, our random number generators are coming from the deterministic two-source extractor. Okay, so this is an old extractor by Dodis et al. It's proved to be secure against quantum side information by Kempe and somebody else. The thing is that this extractor is essentially computing some inner products. Okay, again, highly parallelizing. So private simplification, as I said, you can do it by Trevisan's extractor. Again, it's mostly computing some inner products, significant scope for parallelism. Yeah, so these things can be speeded up with high performance computing and FPGA. So what's the conclusion? So we have got the first practical, resilient, and efficient QPD protocol. So actually, we have 3 variants of BBA. The first one is a strictly one-way protocol. It tolerates S erasures and P bit flips as long as the master equation is satisfied. Okay. We saw, in the ideal case, what this gives. But it's 0.5 erasures or this. You cannot have both of them together. Remember, with the satisfied difference. But some other intermediate figures we saw how you can get. Okay. This also gives us a two-way protocol, but the back communication from Bob to Alice is only constant. Essentially, Bob just informs Alice what is the erasure rate in the bit figure. If you do that, then Alice will use a traditional polar code, which, greatly decreases the computation over this. But SNP have to still satisfy these constraints. So it's almost one way, I would call it, but Bob has told Alice what is SNP. Now, if you want a pure two-way protocol, then again, we know we can do better than BB84, at least in the basis shifting step. So instead of sending n bits for Alice and Bob's basis, we only need square root and polylog. Yeah. So, go to the next thing. For moving further ahead, we can do the similar things with what is called the six-state QKD protocol. So BB84 used the four polarization state. Six state will use left circular as well as right circular. It has better error tolerance. 11% becomes 12.6%, things like that. So we can do the same job with the six-state protocol as for the BB84. Future work will be to improve the bit flip tolerance by using techniques which are actually there in Renner's thesis called noisy preprocessing and advantage distillation. Here, advantage distillation is basically two-way information development and kind of a little bit like the cast. Noisy preprocessing is one way. So using that, I mean, I think if you do noisy preprocessing of BB84, it jumps from 11% to 12.7%, I think, something like that. Yeah, and yeah. So these have been analyzed by Renner, but as I said, we'd like to analyze it with our machinery. Most likely, one will need full permutation variance to analyze it. That's what we're feeling. But given that, hopefully the rest of it will go through. So another future project will be to do a similar analysis and improvement of the Bennett 92 protocol. Bennett 92 protocol, its description is very simple. It only uses the vertical state and let's say one of the diagonal states. It just uses two-state protocol. Of course, it has much lower bit flip error tolerance and all that. The thing is, I'm yet to see a fully rigorous analysis of Bennett 92 for an arbitrary malicious. The proofs that I've seen are for when Eve acts like the depolarizing channel, IIDV, and things like that.
But why do people care about it if it's
a simple to implement. So many experiments like working with it. So just last week, the CDAC announced that they have done the Bennett 92 protocol when there's a fixed base station and a mobile drone. Of course, I mean, the information research, etc., I mean, not the rigorous ones, but they like to implement that. Okay, so now on the experimental side, I mean, this work should spur further refinement of QKD hardware because we're explicitly telling them what are the quality parameters and efficiencies and all that. Okay, and maybe these techniques can lead to progress in studying other crypto things beyond QKD, like oblivious transfer, and that's it. So I should answer your question about the translation. Can I write on that?
Yeah.
So let's say X is some bit string of length, and this is the raw. Now, so these are the photons going in. So the photons are encoding X, but the photon function. So then somewhere, I mean, Eve, she has her own ancilla. So this shows up as, so this is X. This is X prime formations. So there will keep errors. So the location for X and X prime disagree. Now what can happen is, a priori, number of bit flips. Well, whatever that's the probability distribution of bit flips can depend on X. Some strings, mean all zero strings is transmitted with very low bit flips. Some other string is transmitted with high number of bit flips. So apparently this is possible.
that's why you translate to
Yeah, so this is what to make the mathematical analysis very difficult. I'm not sure if you can come up with security proofs that way. At least in our style, coming up security proofs with this, I mean, makes the job much more difficult. I don't know if it's possible. But if you do this translation, so in X goes to some X XOR Y, then goes to all this. Okay. So let's call this X bar, and what bar is X bar prime. So then the point is, if you and now later on Y also gets set, and from X bar prime, Bob can take this and get X prime. Okay. The point is, because of this randomness over Y, averaging over Y, this probability distribution becomes independent of X. So now it's really like a channel. I mean, there's X and let's say BSCP is acting, right? Binary symmetric channel crossover probability, or whatever. So, yeah, so this ensures that actually, uh, rigorously speaking, is a computation invariant probability distribution acting or not, or more precisely, he chooses an error vector from a computation invariant distribution independent of x. She exhausts this error vector e to x, that is the x prime which comes. So that really makes the mathematical analysis simple. So maybe more questions.
So in the one-way protocol, in case the protocol fails and go forwards,
Oh.
there is no way Alice can over. Okay.
Yeah, that's true. Yeah. So this is just to drive home the point that but yeah, maybe more realistically, Bob said one will saying that look, you better have what.
At the end, like how will Alice know which bits to use in this?
Which bits to use for what? I mean,
Like as the final.
for information reconciliation. Which bits have been corrupted?
Yeah, like which bits? No, like which bits Bob has finally decided to use as the key.
No, so actually none of them go. So that's the beauty of this protocol. So actually, none of them work. So okay, so maybe I'll indicate how information reconciliation occurs. Okay. So Alice's log is chosen uniformly from 0 to the end. Okay. Now, do information reconciliation. What happens is, imagine this space. Okay, so this is some group of size identity. Z mod 2 to the power n. Now, your error correcting code is a subgroup of this. So there is a certain subgroup of this. This is the error correcting code. So this is the error correcting code, and these are the cosines. Okay. So think of this 2 to the n strings as broken up into the cosets of the error correcting. Okay. So then anyway, this is all Alice's mind. Okay. The computation what she has done, she just chosen a random x. Okay. This random x is sent as photons. Okay. Then whatever there's E. Yeah, E. Bob gives x prime. Okay. Now x prime is different from x in some locations. So how can Alice help Bob? So Alice, so she has to send this information reconciliation thing. So what Alice sends, so this string, the information reconciliation for x, which of course doesn't know what are the locations. The information reconciliation string that she sent, the IRX, is the name of the coset. So this x, let's say, lies in this coset. Okay. So this will not reveal x, obviously, but Alice will be the name of the coset. So let's say we are given standard names for all the cosets. So now the question, how many cosets are there? And if you count, it's exactly that code. It's plus 1 minus s times h. If you have this optimal code, that's exactly the thing that you. So yeah, so this machinery only works for linear codes. So that was also an issue. We want all these nice codes and they have to be linear. Okay. So Alice sends this coset information. What Bob does is, Bob translates x prime to x prime minus the coset information. Of course, over z1 to minus and plus is the same thing, but I just wrote minus so that you understand that the coset information is removed. Then, essentially, what will happen is that after removing the coset information, so this is what the original x will do. So what is this? This is x minus IRX. After removing the coset information, so this will lie in the error correcting code. Instead of x prime was sent. Then remove x prime minus IRX. The same shit, you come up with a point here. So both of this lie in the error correcting code, and now the error correcting code will correct this point. And then yeah, this and then you add that IRX back and come back out. So you correct this to this. Then and this number. So this is how expand gets corrected back to x at box. Okay. Now, Eve has learned a little bit more, but there is something in x, some mean entropy in x, still lying condition on Eve. And this is the beauty of the extractor. Extractor works with this mean entropy guarantee. Alice does not have to know which bit is known. Okay. So I think what the extractor does is it computes certain linear combinations of all the bits of x. And it turns out those linear combinations will be perfectly random.
And that mean entropy is ensured by limiting the number of detectors.
Yeah, it's ensured by limiting the number of errors. So basically, this quantity is limited, and that mean entropy is that slack which I have, right?
Right.
Yeah. This is the mean entropy which is left, the left hand side. Information recovery further leaks something out, which is here. And that gap is what survives after this. And the maximum that we can extract is the difference of this. That's the slack. And we'll not even extract the total slack. We'll extract a small part of the slack and keep the rest aside to construct a shorter polar.